Hello everyone and welcome back to another video here on the Polaris School of Quantum channel. This video is going to be another one of our famous series, The Hidden Quantum Champions. And in today's video, we are looking at a company called Quantum Design. And without further ado, let's figure out what their role in the quantum technology sector is right away. So here we are on their website. It says Quantum Design North America. There's also, let's say, different locations of this company called Quantum Design. But I'm looking at this one now. You can also search for them on Google. You can see that there are other ones as well. So here's the nice building they have. And you see that they work on a lot of different technologies here. You have people that are assembling these machines, and you can see it looks like very scientific apparatus that they are working on. And actually, here's a products rider, but you can also see the different products that they have here. So there's material characterization, cryogenics, optics, microscopy, NV technologies, education, quantum technologies, sample synthesis, spectroscopy, biotechnology and chemistry, nanoscience, and then applications team as well. So you see there's like various different areas that they are, let's say, working in. Of course, we are going to look at the quantum technologies, but before we hop into that, I also want to quickly jump with you into the nanoscience part, just to show what various areas they are actually working on, and then also maybe empathize why besides what we see in the exact quantum technologies tab, also the other stuff that they are doing here plays a big role. So let's quickly go through the products that we see here. The first one is the Fusion Scope. It's a correlative AFM-SEM microscopy platform. So what is that? Well, an AFM is an atomic force microscope. So how does that work? Basically, you take a tip, an atomically sharp tip, metal tip. You can, for example, achieve that if you take a wire, a metal wire, and then you pull it apart very, very slowly until it rips apart. And what will happen is, if you use specific materials, it will end up in an atomically sharp tip. So there's one atom which is sitting at the front. Of course, it's not like a perfect cylinder. There are other techniques that can get you something that looks much better, also microscopically, but that could be a technique. And then when you take this tip and you attach it to a lever arm like this, and now you bring the tip into the vicinity of a material, there's going to be some force interacting between the tip and the material surface. And this you can actually measure if you point with a laser beam on top of this lever. So you can imagine you have the lever here, the laser beam is shining on it and being reflected back. And with a detector, you can basically measure this reflection path. So how much the tip is being bent up or down. And this technology can actually be used in order to really atomically, precisely measure the change of this tip position. And with that, you can measure, let's say, atomic surfaces. So you can go all the way down to single layer precision. So you could, for example, look at a graphene surface, and maybe you know that if you take graphene, so what is in your pencil, if you take that and use a scotch tape, so you take a pencil, you rub it on a paper, then you take a scotch tape, pull a little bit a part of the material that you wrote on the paper, and then you take a scotch tape on top and you pull them apart, and you do that multiple times, you will end up with graphene, so single layer carbon material, a single layer carbon network, more or less, single atomic layer. And that's something that the Nobel Prize has been awarded to in the past. So with an AFM, an atomic force microscope, you can actually scan surfaces very, very precisely by the atom. So you can measure the height, elongation, and then you can move the tip at very, very small distances, and you do that again and again and again and again, and you scan through a whole surface. And what you end up with is you basically accumulate a map that has a topography map that is atomically precise. Now, this is usually a very, let's say, local method. So you're measuring a very precise, like you're measuring very precisely the height profile of an area, but it is very local. So you cannot scan, let's say, a 1 by 1 meter surface, because if you would do that, it would take you years, right? Because you're moving at such a small distance with the tip. Now here, this comes combined with an SEM, that is a scanning electron microscope. So this is a microscope that, instead of using light, like you know in your optical microscope from the lab, maybe from the school, an electron microscope is using electrons as the light source, more or less. And with that, you can measure all the way down to nanometer scale. So now what you can do is you take your wafer, for example, your wafer with your superconducting circuit and maybe a nanowire Josephson junction, which you need to build some type of qubit. You put it in this system, and then you basically start looking at it with the scanning electron microscope, and with that you can see the whole chip, right? You can zoom all the way out to like a centimeter by a centimeter, so you see the whole chip. And then you can zoom in until you find where your qubit is located, your quantum bit is located, like the Josephson junction maybe. And then in order to measure, let's say, if the nanowire, how high the nanowire actually is when it is positioned on the substrate, you can then probably switch to this AFM here and measure this. So this is like a combined instrument that enables you to do both of it. So here you see the AFM. There's this very tiny tip which can measure the surface properties, and that's actually the tip, I guess, under an SEM, so under a scanning electron microscope image. And there you see there's this atomically sharp tip, and now you are scanning through the surface here, and what you get is these types of images here. So you see this is 20 micrometer by 20 micrometer, but at a resolution of 200 nanometer size. So can measure like very, very small size differences, very precise topographies. And in this case, you see it's copper and niobium. So you can even say what material it is. But also here, nanoprobing. So here, for example, you see these gate fingers here. So metallic gates, I guess. It says also here, nanoprobers, localize electrical information. So you can probably even measure if these gates here are electrically connected. So you see there are these green fingers here. I guess they apply a voltage between those two gates. You can see them with the AFM and then with the SEM, with the scanning electron microscope. You see this is 20 micrometers distance. So these are very, very tiny objects. And then you have this tip here, which you can also use to acquire electrical information, like, I don't know, the electric field, or if there's a shortcut somewhere in between that. And you can already see by all of this that, of course, these are extremely relevant instruments when trying to understand your quantum chip that you are designing, the properties that you are designing into it. Here's another example. You see an AFM insert for an SEM/FIB. So SEM we already had. It's a scanning electron microscope. So it uses electrons instead of light to scan. Now an FIB is a focused ion beam. What is that? Well, actually it is basically using ions, so atoms that have an electric charge by removing, for example, an electron from them. Now they become electrically charged and you can accelerate them. So you can use an electric field to accelerate an ion. And you can actually use that like a bullet. So you can, for example, take your sample, you take your quantum, let's take a nanowire, for example. You have a nanowire in your quantum sample, and you want to see what the cross-section of that looks like. So actually, you would need to cut it off. And this FIB is exactly that. It is an instrument to cut away material, to selectively remove material, but on a nanoscale. So you basically look with the SEM, with the scanning electron microscope, where you're also actually bombarding your sample, but with electrons. These are very light, they don't do any damage. They're also tuned. You can tune the energy at which you shoot them on the sample so that it is, let's say, less invasive. And there's also other reasons why different particles have different, let's say, damage rate. But now let's not go into the details of this. But you take the scanning electron microscope, you look at the surface, you scan it, and then when you find, let's say, the nanowire, when you locate it, you are activating this FIB, this ion source, and then you're shooting ions on the surface and thereby removing material until you are left with a trench that you are cutting into the sample, and then you can tilt the sample surface and actually look with the microscope onto the cross-section of your sample. So here's now the advertisement page of that insert of that machine. And then, okay, here you get, let's say, an AFM tip on top of that. So you can not only cut, for example, a trench, now you can even use an AFM to measure the impact of that. And there are different reasons, different cases where you might want to do that, where you could be interested in combining these different methods. And yeah, that's explained here. There's also other stuff like a quantum magnetometry atomic scale. There's this quantum diamond microscope. I think that might also be something interesting. So a QDM by EUQLID, which is probably another company that we should check out within this series later on. But yeah, this is the instrument, and I imagine that, yeah, you can use probably this instrument to measure very small magnetic fields. Okay, that one here might also be interesting. So the Proteus QTM trademark, a scanning NV microscope by QNAMI, another company that we might want to check out within this series. And this is, I'm now reading from the website, the QNAMI Proteus Q is a complete quantum microscope system. It is the first scanning NV, nitrogen vacancy, microscope for the analysis of magnetic materials at the atomic scale. By combining NV magnetometry and scanning probe microscopy techniques into a single instrument, scanning NV magnetometry provides simultaneous acquisition of the sample's topography, that's what we saw before, right? And its surface magnetic fields with nanoscale resolution, while the tip's radius of curvature determines the lateral resolution of the topography image. It is the distance between the NV center and the sample surface which determines the lateral resolution of the magnetic image. The Prometheus Q system comes with state-of-the-art electronics and software and has been designed to allow for future adjustments, expansion, and capability upgrades. QNAMI's proprietary quantum technology allows you to see directly the most subtle properties of your samples and the effect of microscopic changes in your design for fabrication process. So this, I think, is a very interesting development. So I'm always talking about the quantum technologies as not just quantum computing, right? There's also quantum communication and there's quantum sensing. And I think actually the order should be exactly the different way around, because quantum sensing is, let's say, the first to achieve of those technologies. It is basically creating a quantum system that can not only be controlled precisely, but can also be measured precisely and it be exposed to something. So in this case, we have this nitrogen vacancy, which is basically a nitrogen atom within a diamond. At least usually that's how you create those. And this is now creating, let's say, an atom, nitrogen atom that is encapsulated into a diamond crystal structure, which is a very, very stable, a very solid crystal. So you can actually consider this nitrogen atom as a single quantum system within this diamond, and you can use that to, for example, measure magnetic properties. Usually, I think the way that this is done is you have a ground state of your vacancy of the system, which is like an electronic state, and then you can move up the electron to an excited state from this ground state. And this excited state you can actually reach by, I think, shining green light on the diamond, and then the state will decay back to the original state in actually two processes, and one of them is basically a dark process, so it doesn't emit any light, and the other one is a light emitting process, and that's why you get a red light back from the vacancy. And now what you can do is, if I remember correctly, there's another step in between, which you can excite with microwaves. So you can excite the electrons to this intermediate state with a microwave signal, and then get them up to the main excited state with green light, and then basically watch them fall down with this red light again. Now, if you tune the microwave frequency, you will see that for some frequencies, for a specific frequency, this electron, this intensity is kind of changing, because you're moving the electrons from this lower ground state into this excited state, the microwave transmission, and then all the way up and then down again. And actually now this microwave state, this is a magnetically responsive, magnetically sensitive state. So it has a spin polarization. And now if you apply a magnetic field, actually the state is splitting up in two states. So you can now see that if there's a magnetic field present, you will not just see one dip in your intensity measurement, but you will actually see two. And the distance of those two tips, I think, more or less is a function of the magnetic field that the atom, that the NV center within your crystal is feeling. All of this goes to say there's a way to use this quantum transition, this isolated NV center state, as a sensor for magnetic fields. And of course, because this is an isolated quantum system, which by definition is, let's say, the smallest transition, the smallest system, right? That's the idea of quantum, to be the non-divided smallest thing, right? So a quantum state is, let's say, along the smallest energy transitions possible. And if you can isolate a quantum system and use that as a sensor, you get, let's say, the most precise sensor, or a very, very precise sensor, one of the most precise that you can build. Because there's no smaller transition, so based on the same material, you can build nothing that is more precise. That's kind of more or less the idea. And here you now actually see a system that you can buy, that you can operate, which is using pure quantum mechanics, which is isolating a single quantum system to perform this measurement. That's at least how I understand it now from what I see here. And that allows you to do, of course, the atomic force microscopy that we've seen before, right? Which is measuring the topography, but now you can also measure at the same time the magnetic field. And I guess that's what you then also see here. You can see the magnetic, for example, grain boundaries of a system. So you can see in a system where actually the magnet, so if you, for example, look at a magnet, at a piece of ferromagnetic material, like think about your piece of metal, your piece of iron. If you're taking a magnet, you can actually magnetize that, right? And what happens is, in a microscopic range, you have these different areas that are already magnetic, but in a standard state, like when the iron is not magnetized, these are just randomly oriented. So if you look at it from, let's say, the net sum of all of these little areas, it's basically zero. That's why it's not magnetized. If you take a magnet and you move it along this, for example, nail that you have, then these little areas, they will be started to align. So then suddenly they align with each other, and that's why the why the nail is actually becoming magnetic, because you are taking an external magnetic field and you are polarizing these tiny areas, this microscopic areas, and you're all aligning them into one big magnetic area, which is pointing the magnetic field into a unified direction. And that's why you create this, let's say, net existing non-zero magnetic field. Now, if you apply a hot temperature to this piece of nail, for example, that you have, to this metal nail, it will start to shake all of the atoms, all of the lattice of the metal crystal, which the nail actually is. All of these will start to shake, and then these areas, they will, at some point, if the temperature is high enough, that's I think called the Curie temperature, if this temperature is reached, then you will lose this alignment again. So if you heat up the nail and you take it again, it's not magnetic anymore, because then again, like these little areas, they will start to be distributed randomly again, and then you can take a nail and magnetize them. And with this technique here, you could actually make this visible, because you now have a way to kind of measure on a atomic precision, more or less, or a very, very tiny scale, maybe not atomic, but on a very tiny scale, you can actually measure these magnetic boundaries. So here we see it's like micrometer scale, I think, what we are looking at, single micrometer scale. So that's a very interesting technique, and again, a very exciting technique, because one, it allows us to understand the materials better and manufacture materials better, which is generally interesting, not only for quantum technology, but for all types of things, because actually nanotechnology or nanomaterials are around us almost every day nowadays. But then also, and I mean, I'm really like, think about think about magnets, because we're talking about them, right? Magnets are a big topic nowadays, because we have all of these electric cars that are around us now, and the electric motors in there, they actually partially work with permanent magnets. So designing a magnet with materials that are more available, that are easier to manufacture, that have a better performance, so higher magnetic fields. Stronger magnetic fields means you might need less materials, so you can save money. So there's actually a whole economy behind that, and this type of technology is already available today, can be used, and is being sold. So this is an area of quantum technology that generates, let's say, real impact value already today. And I'm not saying that the other ones don't, but I'm just saying that here you see something that is very concrete and very easy to understand, I would say. Besides that, there are also other things here. I'm not going to go through all of them now, because also I don't want to stretch today's video for too long. Laboratory squids is another interesting one, I think. So a squid is a superconducting quantum interference device. And actually, when I studied physics, I actually had the chance to work with some of those. It is another one of these cases. So it is, again, a quantum-based sensor technology. It's using superconductors to measure very tiny magnetic fields. And I'm reading just from what they are saying here. So Quantum Design's patented high symmetry squid design and electronics provide the most rugged and sensitive all thin film sensors commercially available, and give you everything you need to configure flexible, powerful detection systems for your research. These sensors can easily withstand the rigors of a laboratory environment, such as repeated temperature cycling. Their robust performance offers a level of reliability and adaptability that has earned QD, so Quantum Design, a worldwide reputation as the squid of choice. OEM services are also available for commercial applications. And then you see here some points on that specific one. So this is a single channel DC squid controller. So there's a DC and an AC or RF squid. So that has to do something with the readout technique. And it says low power, low noise electronics in a compact package, enhanced tuning capabilities to ease optimization for low noise operation, compensation for zero temperature coefficient. Very, very quickly on the topic of squid, how does it actually work? So you basically have a circuit, and you have two junctions in there, which are, let's say, they're called Josephson junctions. So they are like isolating junctions. So at the end, what you have is looking basically like this. So you have a circle in the middle, and then you have either two, or I think there's also the version with a single junction. There's also a version with a single junction. And then, so might also look like this, not like this, like this. And then what you can actually do is you can drive a current through this, which is circulating, and more or less you can create a system. Yeah, well, you create a system where there's a magnetic field being, or the magnetic field at these very, very tiny quantum states is quantized. So there's actually the flux, so the magnetic field times the surface area is quantized. And now if you are driving this, if you're driving a little current in this circuit, you can actually measure if there's a flux quantum present or not, more or less, like if there's another one coming in. And that way you can really count the number of flux quanta that is going into the sensor, so you can resolve very, very tiny magnetic fields. I remember in my lab guide back then it said something like, imagine a red blood cell in your body, and a squid can actually measure the presence of the magnetic field of the Earth in this little red blood cell. That's more or less an analogy of how precise these ones are. So they are very, very precise sensors, and there's actually quite a lot of interesting applications for them. Not only in measuring magnetic fields, but also in measuring currents, because if you have an electric current flowing, you can actually measure the magnetic, you can measure the current, or you can actually measure a magnetic field that this current is producing, and thereby calculating back on the current that has actually been flowing. And this can not only be used in materials, it could, for example, also be used to measure the current that is running in your brain. So I've seen actually once one of these setups. It looks like a big helmet with a super big extension on top of it. And in there you have these squids, and they usually have to be driven at cryogenic temperatures. That's why it's quite complicated to get them very close to your head, because they have to be, let's say, at least liquid nitrogen temperature, maybe even colder helium temperature to actually operate properly. And then you have this whole cooling apparatus, but you have these squid sensors sitting close to your head, and they are measuring now the electric current that your brain is producing while you are thinking, and thereby you can map the currents in your brain, which is for medical research or for brain research a very interesting tool, because you don't have to, let's say, cut open the bone of your head, like remove all of the hair, cut open the bone of your head and put something in there to measure, like some companies are doing nowadays with AI, but you can actually measure without destroying anything. So it's a non-invasive technology. And with that, let's quickly check out this company part. So about the company, because we always do that. It says, for more than 40 years, Quantum Design, QD, has been providing technology solutions to researchers in the field of physics, chemistry, biology, material science, and nanotechnology. Established in 1982 in San Diego, California, Quantum Design is the leading commercial source for automated materials characterization systems, offering a variety of measurement capabilities. QD instruments are founded in the world's leading research institutions and have become the reference standard for a variety of magnetic and physical property measurements. Quantum design instruments are cited in and provide the data for more scientific publications than any other instrument in the field of magnetics and material characterization. This means that each year literally hundreds of scientific publications advancing the science of materials use data generated from QD instruments. An essential part of providing scientific solutions to researchers around the globe is to also offer state-of-the-art instruments from other leading manufacturers. These manufacturers are chosen by Quantum Design not only for their innovative products, but also because they believe in the same level of customer satisfaction and support that scientists have come to expect from QD products worldwide. With headquarters in Switzerland, in USA, and offices in Belgium, Brazil, China, Czech Republic, Germany, France, Hungary, Italy, India, Japan, Korea, Poland, Romania, Singapore, Spain, Sweden, Switzerland, Taiwan, Turkey, and the United Kingdom, QD is strategically located in the world's key centers for scientific research, providing local marketing, sales, and technical support. And with that, we are coming to the end of today's video. So again, we have a company that is, let's say, at the very fundament of this whole quantum technology revolution due to their materials research impact, but at the same time also a company that is applying those quantum technologies, for example, with the NV centers. So from my point of view, a very interesting candidate for the hidden quantum champions. What do you think? Let me know down in the comments below. And if you don't want to miss out on the next video, please make sure to subscribe. And with that, as always, stay hydrated and see you in the next one. Bye-bye.